Okay, to kick off today, I thought it wouldn't do any harm for me to go through an example, sort of like we did at the end of class last time. I want to take this group here, a finite group with a lot of elements, 20 from 25 to 36, 30, 100. And I want to write that in two ways, as the elementary divisor decomposition and as the invariant factor. So first thing is factor 20 in prime powers. That's 4 times 5. Let's decompose it this way. Five is already a prime power. 36 is 4 times 9. 48 is 16 times 3. 120 is, I guess that's 8, 3, 5. And finally, 100 is okay. Everybody see how we split these up, right? Just basically taking every number in the prime power. And I'll say something about that. So let's do element 1000. So I'm just going to try to, just so it's easier for me to do bookkeeping, I'm going to go through this in increasing times that I find in the order. Okay, so 2. Well, there's the power of 2. 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 And there's the power of 2. So got a lot of them. Everybody starts equaling 5. And I'm going to do this in decreasing order because it's going to help me better. Let's see what we got. 16, 8, 1, 2, 3, 4. And this is the elementary divisor piece that corresponds to the project. Everybody okay with that? This is also the CLO2 sub. Let's go to 3 next. See what I've got. I've got a Z9, C3, and a Z3. So I've got a 9 and 2, 3. So it looks like that's it. Okay, let's look for 5. Here's what have I got here. Got a 5, 25, 5, and then 25. So it looks like you got 2 25s and 2 5s. And it looks to me like I'm out of 5s, right? I only had to go 5, right? 2, 6, 7. Okay, so this is the elementary divisor. There's only 3 different primes of value order: 2, 3, and 5. This is the CLO2 group. This is the CLO3 group. This is the CLO5. Right?
Yep.
Invariant.
Fortunately, you did most of the work already there with the grouping of the elements, you know.
That's why I grouped it the way I did. Right.
Yeah, that's most of the work done with, you know.
So what you should do is you be greedy and you go through and you suck up the biggest prime powers that you can. So the first group or the first cyclic factor, the largest one, should be product of these. And that's 3,600. Right over. Okay, that takes care of these animals. So notice I'm doing kind of the opposite thing, right? 16 times 9 is 25. Those are all relatively prime cyclic. I can put them together and it's a single cyclic, 3,600. Right. Okay, what's next to that? 8, 25, and 3. So I guess that's going to be 600. Okay, next. Before final 3, let's be like 20. I'm sorry, 16. And now I've used up the 3s. So now I've got Z4, Z5. Let's see each one. And finally, I've got below Z4. This is sort of the shortest way of all this. Cyclic groups. Notice 4 divides 20, 20 divides 60, 60 divides 600, 600 divides 65. This is the invariant factor decomposition. Now, let me emphasize, both of these groups are isomorphic to this crazy thing here. It's just different ways to write this. This was very nice because you've got the prime powers grouped together. So if you're interested in CLO groups or you're interested in particular primes, this is the way to go. This one's the more compact because, by the way, you can read, for example, do you remember what the exponent group is? It is the smallest positive n such that everything to that power is equal to the identity. You can read the exponent off of this one. It's 3,600. Right, everything in this. So there's an element of 3,600, and every other element of the group divides 3,600. So if you take anything to the 3,600 power, you get FP. Or in this case, add it. So 3,600. Okay, everybody see how to do this?
I do. I already worked on that in the homework.
Okay, so this depends on the following fact.
Okay.
That did here. Notice. And I think I've done this in class, but pardon me if I'm wrong. Then we can show that if I have it. Then
Yeah, I guess it is right, you know, because you have all the elements, and of course, you kind of cycles through them, so you're creating a cycle A, B, then you rotate say another one, then another cycle, kind of like that.
here's a quick way to prove this. Can anybody give me a suggestion about how I might prove this? By the way, it's GCD being AB is between 1 is 1.
First off, we need to note that basically the isomorphic thing between, like, basically the one intersection of the elements will all be the identity elements.
Okay. So
Like if you have the intersection between those two, just be identity set.
notice that cyclic. If we can agree with that. So there exists X and Y in C and D of order A, B. Right? This is an important thing about cyclic groups we already know, and that is if you have a cyclic group and some number divides the order of that group, then there has to be a subgroup of that order. So in particular, there has to be a subgroup of order A and B, and they're both cyclic, so there's an element X of order A and Y of order B. So, let me point out that a subgroup generated by X intersect the subgroup generated by Y is what?
The identity subgroup.
I'll put it zero here. Because anything that lives here has to have order dividing A. Anything that lives here has to have order dividing B. So anything living in both of these has to have order dividing both A and B. The GCD of A and B is 1. So the only thing that lives in both of these has to have order 1, which is right, okay. And notice that if you take the subgroup isomorphic to, so subgroup generated by X is isomorphic to ZA, subgroup generated by Y is isomorphic to ZB. When you add these two up, you have to get everything, because if you look at the element X plus Y in here, its order is the least common multiple of the order of X and the order of Y, which is in fact AB, right? Because the intersection of the two subgroups is trivial, and the order of this, since they commute, must divide the least common multiple. So it's exactly that. And this does it because you have two subgroups. You have two subgroups whose intersection is trivial. And you put those subgroups together and you generate everything. This is one of the characterizations of direct product. So ZAB is isomorphic to group generated by X plus group generated by Y, correct sum, which is isomorphic to CA, for instance. So that's why that works. When I said, for example, Z4 direct sum Z5 is Z20, since 4 and 5 are relatively prime, you can just mash them together and call it a single sum.
Yeah.
Okay, any questions on it? Okay, so let me give you just a couple little words before we move on into the next session. Here, 726. So I'm going to expand on what I did just a little bit. I'm not gonna prove this, but I want you all to understand that here. Well, we've done pretty most of this actually. This is the fundamental theorem. Finitely generated theorem. or at least it's my particular statement of it. Any, finitely generated Abelian group then it is isomorphic to the following. Where F is a finite Abelian. And we've already discussed how we deal with a finite group. Remember, the finite Abelian group case we've already discussed in the previous result. It can be written as a direct sum of cyclic groups in a couple ways. You can key on the primes that divide the ordered group, which is the elementary divisor decomposition, or you can do the invariant factor where there's just the chain of divisors of cyclic groups. Where F is a finite group, and that's it. F is called the torsion part of G. And this collection of copies of C that you might tack on is called the free part. Let me point out that any group of this form is finitely generated. Because F in fact is finite, so it has to be finitely generated. And each C is cyclic, right? And so if there's n copies of Z here, you only need n more generators. So this is finitely generated. What I didn't tell you is we've already got finite groups covered. Why are these the only finitely generated ones? So you might think about that because we can do this easily with more machinery than I'm not going to do here. But why is it, for example, anybody give me an example of an Abelian group that's not a finitely generated Abelian group? Was it? Okay, yeah, that's a good. I was waiting for somebody to be a smart aleck and say, just let that be an infinite number of copies, right? I mean, that's certainly one way to do it. Your example is very good. It's quite dramatic, right? The real numbers is in fact uncountable and can't be finitely generated. But the rational numbers, you might think about this theorem and see if you can justify that the rational numbers are not a finitely generated. So, okay, yes.
Does finitely generated just mean that basically that it's generated by
A finite set.
a finite set?
Right.
Using direct product and
Sure. So, let me show you this group is finitely generated. Any element of this group, I can write as an n+1 vector, if you will, as I said, or n+1 coordinates, where the first coordinate is map. Right? And then the remaining coordinates all come out of a separate copy of Z, right? Okay, so let me give you a generating set.
To the number of components is finite.
Type one generator. This is the form F 0 0 0. So I'm gonna let all zeros be here and F come out of the group. Now, there's only finitely many Fs, because F is a finite. Right, so even if I'm very clumsy and heavy handed and list every separate element of F as one of these separate generators, there's still only finitely many. The other generators look like this. There's several of these. 0 1 0 0 0 0 1 0 0 0 0. Notice I've got a 1 in every coordinate. Now, the number of generators here is the number of this, the number of things here, plus this. So I can bound the generators by how many elements there are in F, which is a finite number, plus, because for sure that's separate generators. Right. Yes.
So finite generator.
Yeah, there's certainly infinitely many elements. Well, let me point out, I didn't say this, I should have said this, or the indexing. This could also be no copies, right? So you could just have a negative finite group by itself. That's always finite generator. You can just take all the finite stuff that. If you've got at least one copy of Z, then there's infinitely many elements. It's still a finite generator. Z itself has infinitely many elements in it, but it's generated by one element. Yes.
What is the theory principle that you say? Is right now it seems to read by the government. Is that flat supposed to be the?
I should have written that. I don't know why I did. And G is isomorphic to a finite group direct sum, finite many copies of Z. Okay. Other questions? Okay. We are going to now start a very short chapter. I am going to give you some results. The proofs will be minimalistic at best. This is mostly to expose you to these concepts, which some of you may see later, and they're interesting in themselves. We've talked about some of this. I've used the homework sort of to help us work through some of this, but I'm going to talk about composition series and solvability. These are a couple of places where in solvability, group theory sort of sends its integrals out and is important in some other aspects of mathematics. Composition series are important as well because it turns out every group, well, every finite group for sure has a composition series. And the reason this is important for finite groups is this is where people start thinking about, okay, we can classify all these things, and it's why simple groups are important. Let me introduce you to some of the terminology here. Series. Let's begin by doing some stuff here. If G is a group, and X, Y elements of G, then we can form the commutator this is defined as an X inverse Y inverse X Y. And this is an old friend that we've seen from homework. And C2 notations, this is kind of better derivation. G prime or G super one is the group generated by all commutators. Is commutator subgroup. Now, let me, we talked about this before, but I want to make absolutely clear. If you look at a set of commutators, right? So I can just go through my group, just take every single commutator. And the inverse of this notice this thing is the inverse of commutator as y. Right? Would I agree? And this is the same thing as commutator y. So the set of commutators is closed under inverses. That is to say, the inverse of a commutator is a commutator. And also, one of the things we did earlier in the homework is if you have a homomorphism, the homomorphic image of a commutator is a commutator, right? It behaves well with respect to homomorphism. What is not true in general, it's sometimes true, but not true in general, is it's not the case that the product of two commutators is a commutator. There's no reason to think that if I multiply this commutator by another commutator, A inverse B inverse AB, there's no reason to suspect that you can rewrite that as a single commutator. And that's why the commutator subgroup is generated by, it's not just a set of commutators, it's every word you can form by mashing commutators together. Notice you don't have to worry about mashing commutators in the inverse of commutators, because the inverse of a commutator is a commutator, right? So you don't have to worry about throwing the inverses as well. But you do have to worry about products. What happens if your group is abelian?
Well, that means that
Well, so let me,
the commutator subgroup is an subgroup.
Identity.
right, every commutator is the identity.
Yeah.
That's right.
Commutator subgroup is the identity subgroup.
And in fact, let me probably there. One, two. Let G be a group. X, Y elements of G. And H and G is subgroup. You've actually seen some of this in homework. Two elements commute if and only if their commutator is one. Two. H is normal in G. If and only if the commutator of HG okay, I'm using the commutator symbol, but now I'm not using it on elements, I'm using it on sets, so I need to tell you what that means. I think this is what I mean by this is this is the group generated by little h, little g. These are all commutators, one of which the elements. So this would be H inverse G inverse HG, where the H is in H and G is G. So this thing by definition, this group generated by this Run over this stage. So, next one. Okay, so the second statement is H is normal in G if and only if this subgroup is actually contained in H. You should just look at a commutator and see. A commutator here.
Yeah, it's close under it.
Right, so if H is normal in G, then that means this thing is H, and so this thing is an H, that's essentially it. There's some more details, but you should go for that. Number 3. If you look at F, well. Let's say, if F from G to H is a homomorphism, then F of commutator XY is commutator FX. F1. So commutator behave very nicely with respect to homomorphisms. And so G prime is characteristic. And so G prime is normal. So because of this property right here, the commutator subgroup, all these commutators, the image of a commutator is a commutator, which means that that G prime must be characteristic of G. Right, because this is an odd morphism, this goes into the commutator. So in particular, G prime must be a normal subgroup of G. And this is one of my, yes,
Wouldn't that only be an automorphism, but you can show that it would be true for
this
any
is true for
automorphism?
any homomorphism.
Oh, so it's
restrict
true
this to
for
an
any,
automorphism.
okay.
Right. And finally, and this is actually one of my favorite ways to think about the commutator subgroup, and I'll show you kind of a good thing of this. G prime mod G mod G prime. So in the previous part, we know that G prime's normal. Is the largest abelian quotient of G. And let me be a little bit more specific about what I mean about that. That is, if H is normal in G and G mod H is abelian, then H must automatically contain the commutator. And conversely, if H contains the commutator, then H normal G mod H is abelian. This is kind of another convenient way to think about the commutator group. And let me give you we proved at least 2 of these in the homework. I challenge you to think about this, but the last one, if you take the commutator subgroup, take G and mod out the commutator, that quotient is abelian. And if you take a random normal subgroup and you mod out, then and you get an abelian quotient, right? So G mod, whatever you mod it out by, abelian, that means that we had to contain the commutator subgroup, right? Let me point out, so here's the example. Commutator subgroup. And I'll give you a hint. Now, Lord knows I don't want to sit here computing commutators all day long and try to figure out what the freaking subgroup is when I put all those together, right? Somebody tell me why. There's another fundamental reason why the commutator subgroup is cannot possibly be all of these five. What differentiates something from being A5 as opposed to generally being S5? What does it mean for permutation in S5 to actually live in A5? What's that now? Has to be even, right? Everybody agree with that? To live in A5, you have to be even. Now, this X and Y in S5 can be either even or odd. But what's true about this? This has to be even, right? Because, for example, if X is odd, then the product of these two odds is now even, right? And if Y is odd, the product of these two, in simple, if X and Y are both even, then this is even. So, right, because notice there's an even number, there's a pair of X's, X and its inverse, and a pair of Y's. So this has to, no matter what, this has to live in A5. Right. Well, now, my only choices are A5 and 1. So what's the commutator? So what's that isomer to? I'll give you a hint. How many elements are in this portion? How many left cosets A5 are there in this file? 2. That's right. 2. How many groups of 1 or 2 are there? This is a prime time to answer. This quotient has 2 elements, so it has to be 6 and people. This is isomorphic. C2. Is this Abelian? S5, not Abelian, right? Is this Abelian? You bet. A5 is the commutator subgroup is the smallest normal subgroup since the quotient is Abelian. That's why it's the largest Abelian quotient. Another way to think of it is the smallest normal subgroup since the quotient is Abelian. These are the only 3 normal subgroups. That's the smallest one since the quotient is Abelian. This is A5. What about the commutator subgroup of A5? Now remember, A5 is simple. So there's only 2 normal subgroups, A5 and the identity. which quotient, if either, gives you an abelian group? A5 mod A5 gives you the identity group. That's certainly abelian. A5 mod the identity gives you all of A5, which is not abelian. Commutator subgroup here is A5. Right, and we did that with our knowledge of number 4, just knowing that it is the smallest normal subgroup, such that the quotient is abelian. Okay, any questions on that?
So that, like X, Y, they have to be equal to the elements of A5. When you said that if one of them is odd, like, then the whole thing is odd?
Mhm.
Or like how would, if one of them is odd, the whole thing become odd? Because if, oh, it just,
If one of the, it doesn't matter, it doesn't matter whether these are even or odd and which
Oh.
order. This is always even,
oh, okay,
this is always even. Okay. Any questions? Okay, as promised, we're gonna talk about series, which actually offends me a little bit. I think it should be called sequences, but I'm not old enough to find them. Okay, so I'm gonna define it, what we call series, different, types of series, definition. There were one. Let's let G, be a group. Number 1. I'm first going to define a simple series. Is a sequence of groups. Normal 1, normal G2, normal G10. So it's kind of a ladder of successfully normal groups such that G GK and GK. Oh, I'm sorry, I got the find this, that's one. GK plus 1 is in GK, but for all appropriate K. Yes, I'm sorry, this. So we say it's a central a series if you have this ascending staircase of normal groups. Let me point out, normality is not transitive. So for example, G0 is normal in G1. This does not guarantee that G0 is normal in G2. It just means it's normal here, it's normal here, everything's normal in the next successive step. And if you take the group generated by commutators, GK plus 1, it becomes a subgroup of the previous one down. So all commutators formed from G and G2 actually fall down into this. If G has a central series, we say G is an influence. They use an input from her. uh, for example, you can prove that, well, we get a five. Those are the only normal subgroups of A5, just the identity of this. And notice when you take the commutator of the A5 with itself, it's still A5, it doesn't go down here. So A5, for example, is not null equivalent. Number two, an upper central series. Of G is a sequence of the form yeah, I'm gonna start with, I'm gonna go Z. Normal, Z1. Normal, C2. Normal, ZK. And this could continue on. And I'm gonna tell you how we define CK plus one. Inductively, the C0 is defined to be one. And so how do I get, the next Z from the previous? CK plus one is the set of X and G. With the property that for all G and G, commutator XG is in CK. This is an upper central series that's built this way, to sort of build up. So for example, Z1, how is that defined? Well, Z0 is just the identity. So Z1 be every X in the group such that for all G and G, X, oh, right. So what would C1 be? It's everything in G. So, is X and G such that for all G and G, the commutator XG is in Z0, which is one. Right? That's the way it's defined here. So this is X and G such that for all G and G, XG is equal to one. Can somebody think of another name for C1? It's the center. It's everything in G that commutes with everything in G. Right? So this is the center of G. And hence that notation. But now you inductively build up from that. And C2 is everything in G, such as for all G and G, XG is in the center, and so forth and so on. Build up there. If this so there's actually a theorem here. because, the theorem would be showing that, parts 1 and 2 are equivalent definitions. Okay, this is probably a good place, to finish up. You might look at the next two parts of the definitions, number 3 and 4. I'll go over this next time. These two, the notion of nilpotent is actually equivalent. This is the, central series, and this is an upper central series. And we'll talk next time about the derived series and what it means to be nilpotent, and then get on to the grades. Okay, questions? Yes, sir.
So then, the exam is not next Friday, not this coming Friday, not next Friday, Friday after.
I think it's 7.
Okay, and so the grades will be there, but it won't be extensive.
We'll see what good more takes. How does Wednesday before the exam sound for a review session? I don't want anybody to say, oh my God, tell me now if you want to accomplish. But I was thinking about like 5 o'clock or something like that on, Wednesday before the exam. Look at your calendars and see if that's a mess.